Okay, in this movie we're going to have an object being pulled along the floor um, with like a rope at an angle of some amount, and we'll call this the force that's being pulled. It's going to be pulled at a constant velocity, so other forces we need on this FBD would of course be um, the weight of the object. We would also have a normal force of the object, and then we'd have friction going back this way. And remember, we for our FBDs, we're going to try to put all the vectors on an XY grid, and so this pull force along the rope is not on the grid, and so we would like to replace that with a force going over, which we would call F, maybe X, and a force going up, which we would call maybe Fy. And we need to quickly always figure out, resolve this vector into these two vectors. This Fy is the opposite side of the angle, so Fy would be F sine of theta, and the Fx would be F cosine of theta. And so what do we know? Well, we know that this is going to be moving at a constant velocity is what it's saying. So that means that this force over here, the friction force, and the Fx going to the right, they have to be equal. They have to be equal to each other because there is zero net force. So those have to both be equal to each other. So we can start with that. We could say F cosine of theta equals friction force. And then we know that F cosine of theta, we know that friction force is, the equation for friction is mu times the Fn. And then F cosine of theta would equal mu times, what is Fn? Well, we have Fn is an upwards force. We also have Fy, which is an upwards force. And then we have weight, which is a downward force. And we know that there is no acceleration in the vertical direction. That means Fn plus Fy would equal W. So Fn would actually equal W minus Fy. So in for Fn, we'll be putting W, which, by the way, is mass times gravity. So I'll put mass times gravity in there instead. Mass times gravity minus F sine of theta. Okay, so then I'd have F cosine theta equals, I'll distribute the mu mg minus mu F sine of theta. And then I want to get all the F's on the same side. So I'll take F cosine theta plus mu F sine theta equals mu mg. And then I could distribute out, or take out the F, factor out the F, would be cosine theta plus mu sine of theta equals mu mg. And so I could come up with a derivation here to figure out the pull force right here on the rope, and it would equal mu mg over cosine theta plus mu sine of theta. That's not an equation you have to remember, but like all these problems, what's really good, I think, is to not use numbers. You can do this problem later when you see it in the ELAB or on the competency and plug in numbers, but it's good to just always draw an FBD, start with what you know. We have constant velocity, so these two forces here at the first equation had to be equal. And we just sub things in and rearrange algebraically to solve for what we're trying to figure out. So in this particular problem, you would be given mu, you'd be given the mass, and you'd be given the angle at which we're pulling this object. So you'll be able to plug all the numbers in there and figure out what the force is by using that particular equation. So I'm going to do a lot of lectures on forces, and I'm not going to use a lot of numbers. I'm just going to derive an equation that you could use for that particular problem. Hope that makes sense.